faithfully delivering value, interpreting great books worldwide. Hi, this is Sally's Book Talk. Today, we're diving into the book, The Enchanting Liquid. So, when it comes to liquids, what springs to mind? Think about everyday drinks: coffee, tea, cola, stuff we use, laundry soap, shower gel, perfume, and natural wonders, rivers, lakes, oceans, all liquids. They flow through us and our lives, seeming ordinary but hiding mysterious or dangerous stories. Ever wonder why rain washed windows still get dusty? How do those massive waves come about? Do we really need to separate shampoo from hand soap? What's the secret to brewing a perfect cup of tea? In this book, we'll uncover all these liquid secrets step by step. The author, Mark Miodonic, is a material science professor at University College London, a fellow of the Royal Academy of Engineering, former BBC documentary host, and ranked among the UK's top 100 influential scientists. He's also a science writer who loves sharing material science with everyone, having published the best-selling book, Stuff Matters. And now, The Enchanting Liquid is its sister book. Here, he keeps his classic British wit, using fun stories to highlight liquid's allure. It won the 2018 Royal Society Science Book Prize and was named Financial Times Book of the Year 2018. To study all kinds of liquids, he travels globally for academic conferences. This book chronicles his flight from New York to San Francisco. On this trip, he encountered liquids in the air. First, he went through airport security. His peanut butter, honey, and whiskey were all confiscated. Airline rules ban carrying over 100 milliliters of liquid in carry-on, and peanut butter isn't exempt. You might ask, is peanut butter really considered a liquid? Well, it flows, has no fixed shape, molds to its container. That's what defines a liquid. So, yes, peanut butter's a liquid. The author just had to grumble and accept it. As the plane climbed, on went the journey with risky, intoxicating, powerful liquids showing up. Some you can drink, like everyday use liquids and natural ones. All right, let's follow the author on this fascinating journey. First, let's talk about drinkable liquids, like energizing tea and coffee or intoxicating alcohol. After takeoff, the flight attendant pushed a cart down the aisle. "Sir, would you like tea or coffee?" After some mental wrestling, the author chose black tea, but instantly regretted it. That tea tasted like boiled cola, completely lacking any tea aroma, though honestly, brewing decent tea on a plane is nearly impossible. So what does it take to brew a perfect cup? Tea quality hinges on four key factors: the leaves, water quality, brewing temperature, and steeping time. More aromatic molecules in the leaves mean richer, more fragrant tea. As for the best tea, subjective. Just pick your personal favorite. Since tea is mostly water, water quality dramatically affects flavor. For vibrant tea, use water with some minerals. Too little tastes flat, too much overwhelms the tea's delicacy. The regular tap water works fine if pipes are clean. Otherwise, you'll get metallic notes. Just run the tap briefly before filling your kettle. With leaves and water ready, next comes boiling. Water temperature determines which molecules dissolve, shaping the tea's taste, aroma, and color. Too cool? Flavors won't extract, color stays pale. So what's the right temperature? It differs for green and black tea. The difference lies in processing. Green tea leaves are heated immediately after picking, preserving chlorophyll, hence the color. Their flavors extract easily, so lower temperatures work best, 70 to 80 degrees Celsius. Too hot makes it bitter. Black tea involves sun withering fresh leaves, then rolling and drying. As leaves oxidize, they darken. Some of these molecules react with oxygen in the air, turning tannins and phenols in tea, which are naturally bitter, into more savory or slightly bitter compounds. So for brewing black tea, you can use 100 degrees Celsius water to get a richer, more fragrant flavor. But here's the issue with brewing tea on a plane. Cabin pressure is lower, so water boils at around 90 degrees Celsius. That temperature is perfect for coffee, but it's pretty awful for black tea. Tea has too many key taste components. A small slip can mess up its unique flavor. In comparison, extracting coffee is way easier. The earliest known coffee grinding and brewing methods appeared in 15th century Yemen, using simple mortars and pestles to crush beans, then boiling the grounds in water. In the Middle East, this method is still popular today, often called Turkish coffee. Even today, this coffee making method remains popular and is commonly known as Turkish coffee. Coffee brewed this way has a smooth texture and rich taste, but it loses fruity or chocolatey aromas. Have you ever had this experience when brewing coffee yourself? Does coffee smell better than it actually tastes? That's because during brewing, many aromas that should release in your mouth escape into the air, leaving mostly bitterness and acidity in the cup with fewer scent molecules. To avoid losing too much aroma, keep water around 90 degrees Celsius. It also lowers caffeine concentration and reduces bitterness. Hand brewing takes too long for coffee shops' daily demands. Therefore, in the steam age of the 19th century, a steam-powered coffee machine was born in Italy. This machine is also called the espresso machine. Today, this machine is still widely used in cafes and homes. It heats water to 88 to 92 degrees Celsius, then pressurizes it to about 9 atmospheres, using high-pressure water to extract the richest flavors from coffee grounds. The whole process is super fast, taking just 30 seconds. This means aroma molecules don't have time to escape into the air, so you end up with a balanced espresso where all flavors are perfectly proportioned. Building on that, you can whip up all sorts of variations. Add hot water for an Americano, mix in foam and milk for a cappuccino, or toss in chocolate sauce and whipped cream for a mocha. A big reason it's so popular is that caffeine perks up your nerves and chases away sleepiness. Lots of working folks kick off their day with a cup of coffee, but too much caffeine can lead to sleepless nights and anxiety. On top of that, caffeine's addictive, just like nicotine and cocaine, which are also alkaloids. Once you get into the habit of drinking it regularly, quitting becomes a real struggle. But when we talk about addictive liquids, alcohol definitely takes the spotlight. The scientific name for alcohol is ethanol. And when we say someone's drunk, it's really ethanol poisoning. Ethanol toxins mess with your nervous system, making you lose control and messing up your thinking and movement. So, what happens in your body when ethanol gets inside? It sneaks through stomach lining cells right into your bloodstream, then heads straight for your liver. Your liver can break down ethanol at a steady pace, but if you drink too fast, overwhelming your liver, ethanol spills over into other organs. For instance, it weakens your heart muscle temporarily, making it pump less forcefully and dropping your blood pressure. So that's when you get reduced blood flow to the brain, dizziness, and feeling super sleepy. As blood flows to the lungs, some ethanol molecules slip through cell membranes and get breathed out with carbon dioxide. Breathalyzers work on this principle, testing your breath for ethanol to tell if you've been drinking. Ethanol affects everyone's brain differently. Generally, it calms your nervous system, helping you unwind and feel less stressed. The author says after a tough work week, nothing beats a little drink for pure joy. Plus, drinking does more than just lift your mood. As a dining drink, alcohol is a killer palate cleanser that makes food taste way better. Why is that? When you eat greasy, high-fat foods, wine's astringency cuts through the slickness, resetting your palate to neutral. When picking a wine to pair with food, think about its acidity, sweetness, and aroma, and whether they'll clash with the dish. The author suggests pairing red wine with steak or salmon, high-fat foods, while strongly smoked fish pairs best with vodka, such spirits. On one hand, high-concentration ethanol dissolves grease, clearing away lingering food tastes. On the other hand, spirits have a simple flavor profile, unlike wine with its fruity or herbal notes, so they don't clash with the food's taste. All right, we've covered drinkable liquids like tea, coffee, and alcohol. Beyond the table, you can explore more useful liquids. Next up, liquids in daily life, like soap for cleaning, fuel for light and heat, and the liquid crystals in screens. You might ask, isn't soap a solid? True, but a dry bar of soap can't wash hands. What actually works is soap solution. Way back in 2200 BC, ancient Mesopotamian clay tablets recorded soap recipes. Dissolve wood ash in water, then add melted tallow. After boiling and cooling, you end up with a simple bar of soap. In this process, wood ash and tallow react to form a substance called hard fatty acid salt, the active ingredient in soap. We know oil doesn't dissolve in water. So how do you wash off an oil stain on clothes? Plain water obviously won't do. That's where the hard fatty acid salt comes in. It's hydrophobic on one end and hydrophilic on the other, meaning it grabs oil with one hand and water with the other. If a bunch of these molecules meet an oil drop, say that stain on your shirt, they surround it and work together to pull it into the water, cleaning it up. There are many mediators like soap. Egg yolk, for example, contains lecithin, which also has hydrophobic and hydrophilic ends. Oil and water don't naturally mix, but adding raw egg yolk to an oil-water mixture, thanks to its special molecular structure, combines them to form mayonnaise. Similarly, you can wash hands with egg yolk. Some shampoos even use it as a key cleaning ingredient. Likewise, mustard vinaigrette uses mustard to blend oil and vinegar. All such substances share a common name, surfactants. Whether it's shampoo, laundry detergent, or shower gel, the active ingredient in all of them is surfactant. To create more diverse products, companies have chemical engineers develop surfactants with different functions. For example, some can bleach, work in cold water, or even suppress foam. Well, hearing that, you might wonder, why suppress foam? Don't more bubbles mean better cleaning? If you check the shampoo's ingredient list, you'll likely find sodium lauryl sulfate. It not only cleans grease effectively, but also creates rich lather. However, foam amount has nothing to do with cleaning power. It's purely sensory, making you feel like more bubbles clean better. Dish soap, laundry detergent, even toothpaste often contain sodium lauryl sulfate too. So that foamy mouth while brushing, just signaling I'm brushing my teeth. While shampoo and toothpaste are daily essentials, do we really need hand soap? Hand soap was invented in the 1980s, making it consumes vast palm or coconut oil. Their special chemistry creates shorter molecular chains, yielding smaller, lighter surfactants that foam better. Compared to thick shampoo or body wash lather, it gives hand soap lighter foam. Palm and coconut trees grow mainly in tropical regions like Malaysia or Indonesia. While hand soap production brings steady income, it drives massive rainforest deforestation. Worse, monoculture palm plantations replace biodiversity, destroying wildlife habitats. Truth is, buying hand soap mostly pays for marketing strategies. Honestly, whether it's shower gel, shampoo, bar soap, or hand soap, their cleaning ingredients are nearly identical. So to protect rainforests and your wallet, the author still advocates using plain soap. Another ancient liquid is common fuel, used for lighting before electric lamps, think oil lamps or candles. Dip a cotton wick in oil, leave a tip exposed, light it, and voila, a bright flame appears. Actually, it's not the cotton wick creating the flame, but the oil seeping from it that defies gravity and climbs up. This phenomenon is capillary action, the wick's absorbing pull, a fundamental liquid property. This property stems from liquid surface tension. But where does tension come from? It relates to liquid's microscopic structure. Solid atoms bond tightly and can't move freely, while gas molecules are looser and break away easily. Liquids sit in between. Their molecules move freely, while constantly forming and breaking bonds. Surface molecules face air on one side and other molecules on the other. Unlike internal molecules, they're not fully surrounded. Imagine a human pyramid. Bottom people feel force above and below, but the top person has nothing overhead. This imbalance creates surface force. That's surface tension. This force can support lightweight objects, like leaves floating without sinking, or insects walking on water, all thanks to surface tension. Notice in a water glass, the surface curves down, but water seems pulled up at the edges. Also, surface tension shrink the glass to a less than 1 millimeter tube, and water climbs upward. That's how lamp oil ascends the wick. To find cheaper, brighter lamp oils, people experimented widely. Innovative breakthrough tone, chemists discovered fuel oil extraction from coal. It burned brilliantly, named kerosene. Soon after, inventors studied black oil near coal mines. Crude oil. Crude oil mixes substances, mainly liquid hydrocarbons like alkanes, cycloalkanes, alkenes. Distillation separates them. First separated are small molecule liquids, highly flammable. This dangerous component was initially discarded as waste until people discovered its air-mixed combustion drives pistons. Named gasoline, it became engine fuel. And later, other substances with larger molecules were extracted. They evaporate slower, aren't easily ignited, and release more energy when reacting with oxygen. This liquid is diesel, aviation fuel powering airplanes. Sits between gasoline and diesel. Less volatile, doesn't form explosive mixtures, so it's safer for aviation since it doesn't ignite easily like gasoline. However, when mixed with enough oxygen, aviation kerosene becomes immensely powerful. In the 9/11 attacks, aviation kerosene caused the Twin Towers collapse. After impact, building floors were damaged. Wind blew in, kerosene reacted with oxygen, generating intense heat, over 800 degrees that deformed steel structures and led to collapse. Aviation kerosene is like the genie in Aladdin's lamp, packed with power to fly you anywhere. But it has a dark side. Burning kerosene emits CO2, heating the planet and causing climate havoc. But the author, flying high, isn't dwelling on this. He lowers the window shade to watch a movie clearly. Next up, liquid crystals and screens. Liquid crystals hide behind screens. We see them daily, but barely understand them. You're probably more familiar with crystals, where molecules align in ordered patterns. Like rock candy from crystallized sugar water. Liquids have random molecular motion. Liquid crystals bridge the gap, dynamic yet flowing. That their molecules align uniformly like fish swimming in sync, a liquid with crystal-like order. Hence, liquid crystal. Polar molecules with positive and negative charges attract to align neatly. This polarity also lets them respond to electric fields. Applying voltage controls their direction. That's how LCD screens work. When you adjust liquid crystal structures with electric fields, you control light passing through. That's how black and white screens work. Change the field, and the image moves. So how do liquid crystals create color? On a palette, mixing red and blue paint gives purple. Mix blue and yellow, you get green. With 3 primary colors, you can create any hue. In painting, primaries are red, yellow, blue. Mixed evenly, they make black. But light primaries are red, green, blue light. Combined, they make white. That's why color LCDs use this principle to control hues. Each screen pixel has 3 color filters transmitting primary lights, red, green, and blue. Just adjust light through these filters to create rich colors. Your phone uses LCD too. Try this. Put a water drop on your screen and look through it. The drop acts like a magnifier. Can you spot red, green, and blue pixels? Beyond cleaners, fuel, and ink, your pen, office printer, even AC units hide liquids. We harness their properties to serve our lives. Yet nature holds untamed liquids, clouds, seawater, lava, creating breathtaking scenes or disasters. Finally, let's explore nature's primal liquids. As the plane descends into clouds, white mist envelops everything, making you wonder, how do clouds form? Think about wet clothes on a line, puddles, your sweat, oceans. Every second, water molecules escape from clothes, puddles, your skin, seas, lakes, and enter the air. But though air fills with water molecules, you see nothing at first. It stays transparent. As more gather, they condense back into liquid. These tiny water droplets slowly gather and are lifted upward by air currents, forming clouds floating in the sky. But for water molecules to form droplets, they need help from tiny particles like dust in the air or factory smoke. Water molecules first bind to these. They attract more water molecules, meaning droplet cores are actually fine dust particles. That's why collected rainwater leaves sediment, and dried rain on car windshields or windows leaves fine powder. No rain nourishes the earth, it sometimes brings disaster. Burning coal produces gases like sulfur dioxide. When clouds absorb these and rain falls, it becomes acid rain. Acid rain acidifies rivers and soil, kills fish and plants, and corrodes buildings and bridges. While acid rain's damage creeps in slowly, like boiling a frog, tsunamis swallow people instantly. On December 26, 2004, tourists in Phuket, Thailand, strolled beaches as usual when they noticed the sea rapidly receding, exposing submerged rocks and stranding boats. Then a massive wave surged, no ordinary wave, but a tsunami. Hours before, the Indian Ocean's crust had ruptured, causing a magnitude 9 earthquake. The quake fractured tectonic plates and lifted the seabed several meters. About 30 cubic kilometers of water, equal to 10 million Olympic pools, was displaced. It raced oceanward at near jet speed. As waves near shore, shallow water slows them but increases height. This is shoaling. Beachgoers first saw water being sucked seaward. Had they recognized this sign, they'd have had about a minute to flee. Sadly, most didn't understand. A 10-meter wave devoured everything. Why would Earth rage so suddenly? The seemingly solid ground beneath us isn't that sturdy. It started as a ball of hot liquid. After 100 million years cooling, a thin, rocky crust formed, averaging just 17 kilometers thick. At Earth's core lies a solid metal heart, over 3,000 kilometers wide. Between it and the crust flows a metallic ocean, 2,000 plus kilometers mantle, where volcanic lava originates, mostly iron and nickel. This flowing liquid creates Earth's protective magnetic field against solar winds, yet also causes earthquakes and eruptions. Since the crust floats on the mantle, it's not solid but separate tectonic plates, all constantly shifting. When plates collide, they silently build pressure until rupturing, releasing colossal energy instantly. That's an earthquake. The 21st quake, triggering Japan's tsunami, equaled 25,000 nuclear bombs. But energy buildup doesn't always quake. Rock creep, like squeezing paper, releases pressure upward, forming mountains. The Alps and Himalayas formed over eons of slow movement, all powered by Earth's fluidity. To thrive here, we must master coexistence with liquids. All right, that's our liquid tale. They're natural double agents, stuck between solid and gas. For millennia, we've tried controlling this state, thrilling yet powerful, yet chaotic and destructively efficient. Today, we largely harness liquid power while shielding ourselves. We believe our bond with liquids will deepen, adding fascination to this mystery. All right, that concludes The Enchanting Liquid. Reading notes below. See you tomorrow.